Our fourth conic section and last conic section that we are going to study is the parabola. As I said at the end of the last video, we have already studied parabolas. We studied them from sort of an algebraic perspective. We looked at a lot of things, graphing parabolas, and some applications of that with like that, we saw that picture of the diver or the ball being thrown up in the air or whatever. Here we are going to consider a more geometric view and sort of a definition, a slightly different definition than what we saw back in Unit 3. Our definition of a parabola here is the set of all points that are the same distance from a fixed line, which we call the directrix, and a fixed point, which we call the focus. You can see in red here, this point P on the parabola is D away from this focus, and it is D away from the directrix. This will always be a right angle. You always want to drop that down at a right angle because that's the shortest distance to that directrix. So that works for that point P. It also works for a point here. If you looked at this distance compared to this distance, those will be equal distances. And that will be true of any point on the parabola. Even if you go way up here to this point and then drop it straight down there, that distance will equal this distance. True for every point on the parabola. Here is how we picture our parabolas. You could have a horizontal parabola or a vertical parabola. They're very similar, except that if your parabola is horizontal, this is not a function of y in terms of x, right? You are going to have a y squared term. Remember, our traditional parabola will be of the form y equals ax squared plus bx plus c, or you might see it as y equals a times x minus h squared plus k. Either of those forms, in that case, the x is squared, the y is not, right? In both whichever format you're in. That's our standard vertical parabola. The x is squared, but it's the only thing that's squared. With our circle, our ellipse, and our hyperbola, both x and y were squared. Down here you can see we are writing this parabola slightly differently here. Back in Unit 3 we isolated the y, right, to treat it more like a function. We're not really thinking of conic sections as functions. The only conic section that is a function is these vertical parabolas. So our focus is a little bit different here and our approach is a little bit different. Hopefully you can see that the vertex will still be HK, whichever format we're in here. This 4P will be the coefficient on the non-squared term, whichever format we're in. If 4P is positive in this situation where the y is squared, it opens right. If it's negative, it opens left. This should probably not be a surprise to you. If you took this to try to solve it for y, you would get 1 over 4p. You'd have to divide both sides by 4p times that x minus h squared, and then add the k over, would equal y, right? That's very similar to the format that we had here. This is our new a. And so because of that, but we like it in this format because we get a lot of information from that. But because of that, the p and the a behave the same way or tell us the same behavior about the parabola. If a was positive in either of these formats, it opened up. So if 1 over 4p is positive, which would be the same thing as 4p being positive, it opens up. And the same is true about it opening down if it's negative. just like we did with the others, I'm not going to memorize these. We are going to figure that out from a picture. When we talk about the length of the lattice rectum, we are talking about the line segment that passes through the focus that intersects the parabola that would be parallel to the directrix. Because we could have a lot of lines that pass through there, at a different angle, but it needs to be parallel to the directrix. The length of that will always be the absolute value of 4p. P could be negative. That's why we need an absolute value on that. Let's look at this. So let's find the focus and directrix of the parabola given by y squared equals negative 12x, then graph the parabola. If the y is squared, that means it opens left or right. Because this number is negative, that tells us that it is going to open left, which hopefully makes sense to you. Okay. We do not have anything added to the x or y here, so we are talking about a vertex of 0, 0. I'm going to go ahead and plot that point right here. It opens left, so we're going this way, something like that. We need a little bit more information, though, to help us graph exactly what that looks like. That number in front of the x, the negative 12, is equal to 4p, which means p is negative 3. P represents the distance from the vertex to the directrix and to the focus. Because it opens left and right, my focus will be to the left. The vertex curves around the focus, kind of similar to the behavior that you see on the hyperbola. So we're going to go 1, 2, 3 spaces here. That means my focus will be at negative 3, 0. The directrix will be 3 spaces to the right, but it's a line. I'm going to draw it as a dashed line. So that is my picture of my directrix and my focus. I found the focus. The directrix is a vertical line. In this case, vertical lines are always x equals a number. Specifically, no matter what y is, x is always equal to 3. So there are those, find the focus and the directrix. The only thing we really still need here is to graph the parabola. I think the most helpful thing to graph the parabola is to use the length of the lattice rectum to tell you the width of this. The lattice rectum has length equal to the absolute value of 4p. Oopsie. In this case, the p is negative 3, so 4p right here is negative 12. Absolute value of negative 12 is 12. That's the total length of the lattice rectum. That means it's 6 each way. So from the focus, notice on our picture here, just to give you a real clear picture, we're opening to the left, so we're talking about this. The lattice rectum goes through the focus. So from the focus, I'm going to go up 6. 1, 2, 3, 4, 5, 6. And down 6. 1, 2, 3, 4, 5, 6. 6 because it's 12 total, so 6 each direction. And so then draw a nice parabola from that. Okay, that's our graph. The picture's a little goofy looking because parabolas are still symmetric over that line of symmetry that goes through the vertex. Okay, I kind of like this in helping us draw parabolas, especially when there's a shrink or stretch factor. It really can make a difference in helping us determine that width. All right, here we have a picture of a parabola. It asks us to find the vertex, the focus, and the directrix, and write the equation of the parabola. Start with the vertex. That appears to be at 3, -2. It opens up. That's an important thing. The focus appears to be at 3, -1. The directrix is a horizontal line where y is always equal to -3, no matter what x is. Let's do this. This distance here and this distance here are equal. They are both 1. That is my p. That is the definition of p. If you go back up to looking at vertical parabolas, we use this equation, x minus h squared equals 4p times y minus k. We just need to plug in what we have here. H is 3. That comes directly from the vertex. P we said was 1. K is -2, so that'll be plus there. One thing to be very careful of, keep track of the sign here. If this had opened down, the P would be -1. Cleaning this up, we have x minus 3 squared equals 4 times y plus 2. That's our equation of our parabola. I'm just making sure we answered all the questions. Write the equation of the parabola, find the vertex, the focus, and the directrix. We did all of that. All right, we got one more here. Find the equation of the parabola with focus 2, -1, and directrix y equals -5. I like having a picture. Y equals -5 means a horizontal directrix down here. 2, -1 is here. That's my focus. One thing to remember is that the vertex is equidistant. The vertex is a point on the parabola, so it has to be equidistant from the focus and the directrix. It has to be right in the middle of these two. If the focus has y value of -1 and the directrix is at y equals -5, the vertex has to be at 2, -3. Same x value as the focus, but halfway between the -1 and the -5. I know that this parabola opens up because it has to curve around the focus away from the directrix. We want to write the equation. If it opens up, we are looking at x minus h squared equals 4p times y minus k. I just remember that because if it opens up or down, we can treat it similarly to what we looked at with parabolas back in the previous unit. and know that the y has to be to the first power and the x has to be squared. I know I have to, just like with all of my other conic sections, to get my center, I've got x minus the h, y minus the k. And so then you just have to remember that that 4p goes on the non-squared term, is multiplied by the non-squared term. Our vertex is at 2, -3. That means we're going to have x minus 2 squared, and y, it'll be plus 3. I just need to know what the p is now. Remember, p is the distance from the vertex to the focus. Distance of 2. P equals 2. So in this place, I'm going to put 2. X minus 2 squared equals 8 times the quantity y plus 3. I don't even need to graph the actual parabola. I was just asked to find the equation of the parabola. That's it. If you wanted to graph it, you could graph it by going out 4 spaces each way, because the length of the lattice rectum is 8. 4 spaces each way from the focus, and that would give you the width of this. Remember, we had the vertex of a parabola given in this form to be -b over 2a, and then f of -b over 2a to get the y value that goes with that x value. Well, if that's true, we can use that to help us if our formula, our equation, is given in a different form here. We could complete the square to get it in that standard form, but we don't necessarily need to. The vertex here, or the h at least, will be -12 over 2 times 2, which is -12 over 4, which is -3, and then k will be 2 times -3 squared plus 12 times -3 plus 5. What is that? 2 times 9 is 18 minus 36 plus 5. That's going to be -13. The vertex is -3, -13. To graph this, because of that -13, I think I'm going to go by 2's here. 2, 4, 6, 8, 10, 12, and so on. 6, 8, 10, 12, 14. So -3, -13 would actually be right in the middle of that box, right? Because this is -2 and -4. So halfway in between -12 and -14. -13. -12 and -14. Halfway in between there. Okay, that's my vertex. Now, if you look at our standard form, this is also a parabola that opens up. If you look at our form that we're considering now, x minus h squared equals 4p times y minus k. We talked before about how if you rewrote this, the a is equal to 1 over 4p. If you solved this for y, divide by 4p, add the k over, the a will be 1 over 4p. In this case, that means 2 is equal to 1 over 4p, 8p is 1, or p is 1/8. That tells me the p is 1/8. I know this opens up. That I knew from Unit 3. My focus is 1/8 above. I can barely even graph it because with a scale of 2, they're going to be right next to each other. But it's above the vertex by a value of 1/8. That means the x doesn't change, but we need to add 1/8 to -13. That gives me -12 and 7 1/8. This is an interesting set of numbers here. Small, small, small numbers. -3, -12, and 7/8. Just adding 1/8. The directrix will be horizontal line, y equals -13 and 1/8, because I'm going 1/8 below the vertex, right? And so if I was at -13, 1/8 below that would be -13 and 1/8. It asks us to graph this. Remember the length of the lattice rectum is absolute value of 4p. So in this case, 4 times 1/8 is 1/2. That means my total length of my lattice rectum is 1/2. So I'm going 1/4. This is super narrow. It might help to graph the y-intercept to help us, which is 5, right? If x equals 0, y equals 5. So I'm going by 2 is 2, 4, halfway between 4 and 6 there. Pick a symmetric point over here, here. Super, super narrow parabola. Okay, did we find all the things it asked for? Focus, vertex, or focus, vertex, and directrix, and we sketched the graph. Very good. Applications, we're going to go ahead and do a separate video for that just so we can take a mental break.